So last but not least, we're going to have Rick Bartow, who is a senior management for Lockheed Martin, senior manager in the Applied Science Lab for Lockheed Martin. He is in the Physics and Computational Technologies Research area in ETL, with research portfolio that spans materials, manufacturing, information technologies, quantum sensing, laser material interactions. And before joining the Advanced Technology Lab, Rick has worked at several other Lockheed business units, including their Space Systems, Advanced Technology Center, where he was a key member of their research team developing wide broadband nonlinear optical polymer modulators for RF communications. So then his background is in chemical engineering, a PhD in material science from Stanford, and focused on near IR optical loss, structure property relationships. So thank you, Rick.
Thank you. Thanks to Dave and Syria for inviting me. I really appreciate it. I'm really excited about the opportunity presented by the Big Data Hub here. I expect we will be a strong supporter and participator. I'm going to talk today. I really want to thank the previous speakers because you guys really set this talk up for me nicely, and I will be able to speed through some of this. But I want to also give props to our friends from Pratt & Whitney. A lot of those systems you saw up there were Lockheed Martin, legacy fighter, second, third, fourth, fifth generation fighters enabled by very innovative materials and design practices by Pratt & Whitney, particularly the lift fan for the F-35. So Lockheed Martin is sort of a federated, has a federated business structure. We have these four primary business areas: aeronautics, which is more well known to most of you. Do all manner of third, fourth, fifth generation fighter systems, air transport, missiles and fire control is a pretty diversified business area, spanning fire control systems, seekers, tactical missiles. This is third one across is a relatively newly reorganized business area called Rotary and Mission Systems, with the integration of recently acquired Sikorsky. So this includes all of Sikorsky's rotor systems, as well as naval combat radar systems and a number of other marine-based technologies. Space Systems expands civil, military, and exploratory space missions, as well as strategic missiles. Very, very broad portfolio in large GEO and LEO-based space platforms. So who are we? Advanced Technology Laboratories is the smallest of the research organizations within Lockheed. We have about 230 some odd people. We report directly to our corporate technology office. Lockheed, ATL is legacy RCA. We were one of the original RCA labs dating back to 1929. Our laboratory is chartered with looking way out on the horizon, ahead of those four business areas I showed you. For the most part, we do not touch product. We are the sort of searchlight, much the way DARPA is. We look out generation after next technologies, both for discriminating new capabilities as well as understanding the risk of new technologies for our businesses. So, why we're here today? Four key challenges that were set forth by the Materials Genome Initiative. I think significant progress has been made over the course of the last 5 years, leading a culture shift in materials research, integrating experiment, computation, and theory. We're seeing great examples of that from what we saw in the previous talks, making digital data more accessible, and creating the next generation materials workforce, many of which you folks in the room here are going to be responsible for. So this is, you've seen different versions of this from the other industry folks, Siemens and Pratt & Whitney. Why does it take so long for us to get to new materials in our systems? Well, this is a very, very overly simplified version of the materials to manufacturing design process. We spend a significant amount of time going through conceptual structure design, material selection, material qualification. If it were only that simple and costly, we could almost bear that cost and make it inside the windows for new system or platform design. But this right-hand side of this process verification, assembly, integration, and tests, parts certification, structure certification, leading into low-rate production, that's really where significant costs occur on the order of $50 to $100 million, spanning up to 10 years. That's what we're trying to short-circuit via the materials genome. So what's the design opportunity? Our current manufacturing and design practice is very, very brittle, very sluggish, very stovepiped. There's a lot of resistance to adoption of new materials. We see additive manufacturing as offering a huge potential to allow us to adapt rapidly to our customers' changing threats or needs with highly integrated functionality, embedded functionality in the same structure. Designing our thermal, optical, RF, structural systems together into more tightly integrated components. So this is, again, looking as a searchlight, trying to predict the future. What will the future look like for additive manufacturing? This is not meant to be representative of all opinions across industry. This is a potential picture of the future of additive. So we envision the potential of an exploding population of globally distributed machines working together with advanced forms of current day manufacturing processes, subtractive, formative processes. A completely digitally networked enterprise across the globe with the seamless routing of digital design to build instructions, as we saw with Pratt & Whitney presentation, a digital thread that extends out to our supplier network, to a new service ecosystem that we envision sprouting up. And an ever-expanding global supply chain. The Amazons, the UPSs of the world are only going to keep expanding and creating new capabilities for us to tap into to enable things like drop shipments to forward operating bases or forward deployments, to be able to drop ship things like intermediate builds, custom tooling, custom feedstocks to terminal manufacturing locations. So what does this look like? This is very cartoonish, I apologize. I want to draw your attention to the right-hand corner. So this is the web of design we envision, where we see a very highly collaborative new design community, both within Lockheed, with our partners, and with a new service ecosystem of design tools, validation tools, quick turn sort of simulations, allowing us to do quick turn virtual tests and feedback to our design community. That should allow much more rapid networking and distribution of test patterns, again, out to an envisioned service network of service providers to do first article printing or prototyping and testing. Once we get through that process, we can go into a more secure network where we can either job out components of the subsystem to trusted partners or send the print instructions directly out to a deployed forward operating base. So what does MGI facilitate? We see the foundational framework being developed by MGI is developing, enabling additive manufacturing software, new computational tools, new analytics to radically reduce the cost and design cycle to get us to shrink that 10-year timeline that is so typical for the DoD. Rapid, what so-called composable design, automation, and optimization. What we're looking for are new frameworks. We really need help from the computer science and data science community. I think this is a great idea to host this workshop here in the computer science building. We really need help in how we frame design workflows. You think about harking back to the days of how the internet developed. The internet had its single greatest impact after workflow software came on the market. Simple tools that we're all familiar with today, like Word and Excel. That's when the real payoff of the internet occurred. I think the same thing will be true in 10 to 15 years in this world. As new software tools and frameworks evolve and become usable, as Bryce pointed out, it needs to be accessible to the novice user. Materials people, with apologies, I'm one of them, are not the best at building usable tools for novice users. Virtual validation in selection and execution. Again, in this idea of a new service ecosystem building up or evolving, we envision the possibility of new business models for service providers to provide virtual validation tools and actually running them on a rapid turn basis. And then finally, human-machine interfaces. This is another big role for data science on machine learning and artificial intelligence. How the expert designer, materials engineer interacts with our systems, our new software systems. That's a huge challenge in the world of human-machine teaming and autonomy. That's a big research thrust for our company. Integrated computational materials engineering is being embraced, I'd say, by the industry. This is a representation of ICME that came out of one of the TMS working groups that Chuck helped sponsor. The ICME framework is going to help streamline workflows, streamline data flows. There's always going to be a need for experts on the loop in the so-called OODA loop cycle, observe, orient, decide, act, kind of a cycle, enabling concurrent material and product design in the design cycle. What are the critical technology needs? We need fast-cell, so-called design decomposition tools and optimization. What do I mean by design decomposition? Instead of the Pentagon or the Air Force coming to its industry partners and saying, I need this with these specific brittle requirements on a spec, our customers would collaborate with us in determining what are the mission needs and decomposing those needs down to a set of design primitives that can be configured logically and then optimized through techniques like topology optimization, generative design, computational tools that allow us to build from the ground up rather than presupposing what that design should look like. Robust and virtual rapid validation and verification. That's going to be crucial in the world of additive manufacturing. Error assessment and remediation at all points across the digital thread. The ability to interrogate parts as they're being built, digitally render them, and assess where the errors are and do on-the-fly error correction while we're building. A new ecosystem for web-based platforms, environments, interoperability protocols, machines talking to computers, designers, collaboration tools and design libraries are going to be huge enablers for additive. And then finally, computer-aided new CAD tools for additive manufacturing. They're woefully inadequate today for additive manufacturing. All the tools that are on the market, for the most part, were built for subtractive manufacturing processes. There's a big role for materials data in the intersection of design and analysis. Data science needs for additive. Design abstraction and optimization. This includes techniques like heterogeneous representation. These are mathematical representations of structure, form, multi-scale properties, multiple materials. We need multi-scale physics, geometry, and architecture optimization, and compensation all throughout the process for error and uncertainty. New virtual validation and verification tools. Selection of the ability to decide in the universe of available simulation tools, which are the most appropriate for the design problem. Which ones, how do I string those together into a workable software framework? We need new gold standard data sets for validating materials in additive manufacturing. We saw the microstructures from Pratt & Whitney on what our microstructures look like when we put them through processes like selective laser sintering. They are not the same material. New V&V requirements, new and corrective feedback to the design as a result of rapid turn simulation. And then finally, the human-machine interface, conceptual design assistance to the expert, being able to interface all throughout the design optimization, and then finally, the final design outcome assessment. Is it real? We're always going to need an expert to lay eyes on our machine-driven solutions to make sure it actually makes sense. Word about informatics. Again, just another picture of our view of informatics. Basically, computational approaches to interpret materials science and engineering data. These are data-driven modeling, top-down modeling approaches. Relies on the development of meaningful multi-scale process and structure descriptors. So we're not going from process directly to properties, which frankly is in common practice in the aerospace industry today. We'd like to get to adoption of these data science and informatics tools to help us do more statistical, uncertainty-based connection of process to structure to properties. We have been at work developing an in-house informatics tool within Lockheed. I think this is complementary to Citrine. We call it the Materials Data Mining Modeling and Management Tool. That's a mouthful. It allows us to, it's a very adaptable tool for very different materials domains, very different manufacturing process domains, for looking for trends in data sets, for product performance, finding hidden relationships in our highly dimensional sparse data sets. As much as I'd like to think we're dealing with big data, I think it's big D, big dimensional data. We have a number of analysis algorithms that run in series or parallel for prediction of results based on various inputs, as well as providing guidance, really rapid guidance to the experimentalist. And significantly, informatics provides ways to visualize the data. I wish I'd had this tool available to me 15 years ago when I was looking at massive data sets for my own PhD. I think it would have really provided insights that I might not have ever seen. What do we need in the workforce? So this is, a slice of what I foresee as being highly valuable tools for the free additive manufacturing ecosystem. So design abstraction and optimization, multifunctional conceptual design and automation tools. This is going to be heavily drawn upon from the mechanical engineering, electrical engineering communities, as well as the computer science and data science communities. Multi-physics, multi-scale topology optimization will play a crucial role in design optimization. Validation and verification, the ability to include uncertainty quantification in our models, in our design, and we're still going to need significant expertise in structures and systems, complex structures and systems certification. Human-machine interface, we'll need to draw upon the organizational and industrial psychology communities, as well as machine learning and design systems models. Future needs on the engineering side, I'm not going to go through all these, but much the way ICME is advancing, our government partners are advancing ICME through foundational engineering problems. I think the same can be said for MGI. Realistically complex challenge problems to advance the field, to advance the state of the art, indexing and describing the vast range of different additive manufacturing machine types, their interactions with materials, new operability protocols and constraints. There's a lot of work going on today in developing process simulations for additive manufacturing. There's not enough, in my view, of material interactions being included in those simulations. Experimental data crossing the various families of additive manufacturing technologies and materials. The Citrine database could be a suitable platform for capturing the vast sets of data that are being generated in various test beds like the national labs. Research, advanced methods, I'm repeating myself, in design decomposition. I think there's a lot of work going on in the geometric math academic community there. I think we need to pay attention to that. There's lots of great science and tool sets coming out of that community. Adaptable multi-scale design optimization, uncertainty signature determination techniques. So it's not just, I think there's a role for uncertainty in helping us characterize our processes. You think of it as a tool, not just something we're trying to constantly reduce. Using the uncertainty signature as a diagnostic for how our materials are interacting with complex geometries in additive manufacturing. Culture shift. So within my industry, I think we're going to need to see the development of requirements becoming a customer-company collaboration. What I mean, our designers need to be working closely with our customers, breaking down this idea of static material spec sheets, like you saw in the Pratt Whitney presentation. We need better descriptors of our materials, and that can arise from informatics tools. Requirements themselves in embedded multifunctional designs need to be traded and optimized, because the solution may be a trade-off between requirements as we go through the optimization. We need new methods for design representation, new common data formats between design and analysis. Today, they're hideously incompatible. The design CAD data structures are frankly leaky. They have imperfect interfaces at boundaries. If we could find some other way to represent geometry that's suitable for finite element analysis, that would greatly speed up. We have some efforts in aerospace that take months or up to a year just to do those types of transitions. Radically new analysis methods like B-spline, T-spline, I think we need to be open-minded about some of these newer analysis tools. Data sharing, I think, could be promoted by a sprouting up of new service models for design collaboration, optimization, and validation. So I can envision a future collaborative or commercial service enterprise. Like I said, I've got in quotes here, let 1,000 citrines bloom. That model could work quite well for a number of other types of services. I think citrine is really on the front line for that type of model. And that's, I think they're going to be a great test case for this. Material science and engineers need to begin to think of themselves as data scientists and architects, embracing mathematical optimization, topology optimization, statistical representation. Think of uncertainty as your friend. It's a way to better understand your performance. It's a way to better provide more robust designs. And it's a way to help you better understand the interactions between the material and these very, very complex additive processes that create defects. So in summary, Materials Genome has done a remarkable job, in my view, of creating a foundational support infrastructure for innovation across the design, manufacturing, materials development areas. The future enterprise for additive manufacturing, I think, could be a potential driving force and adopter for MGI-derived materials in data science. I think there could be a number of new research opportunities through the formation of research test beds that are networked between additive manufacturing facilities, compute clusters, and design communities, including materials and mechanical engineers. How do we accelerate the fostering of new business models? I think industry, academia could be in tighter partnership with venture groups to accelerate new types of business models for software support, for validation services, for simulation services. There really needs to be much greater engagement, like the type that's being fostered here in the Big Data Hub, between the materials and manufacturing communities and the data science communities. I live in the world of people that do IT and data science for a living. I'm in the minority. I'm completely surrounded by it. That community has a lot to offer. They're very creative. They're very innovative. I think we're going to see a lot of really exciting creative ideas coming from this computer and data science community. That's all I have. Thank you.